Gambling feels unpredictable, but with the right tools, you can measure how good or bad a bet is. In this video, we'll walk through 3 methods that make that crystal clear. Let's dive in. People say the house always wins, but most of us heard that from movies, TV, or some friend of a friend's story that sounds like an urban legend. So when we hear it, we tend to imagine all the wrong reasons. We picture hidden magnets under the table that detect where you put your chips and then magically steer the game away from your bet. Or we imagine old-timey gangster types lurking in the back, ready to intimidate anyone who gets too lucky. Or we imagine something like a cold deck, the idea that casinos are secretly arranging cards in the perfect order to guarantee you lose. All of these make great movie scenes, but none of them explain why casinos actually win. The real reason is much simpler and honestly way less exciting. Casinos win because the structure of the game gives them a built-in advantage, and that advantage doesn't depend on technology, intimidation, or cheating. Let's look at 2 simple hypothetical games. Both games cost $10 to play, but they work in different ways. Game 1 is a die roll. You roll a standard 6-sided die, and you win only if you roll a 6. If you lose your $10. If you win $45. Game 2 is a wheel spin. The wheel has 4 red slots, 4 black slots, and 2 green slots. You win if you land on red. If you lose your $10. If you win $17. So those are the rules. 2 games, 2 payouts, same cost to play. The question is, which one should you play? And more importantly, how do you figure that out? In this video, we'll look at 3 different methods to answer that question. Let's start with the first, simulation. A simulation is exactly what it sounds like. We pretend to play the game over and over and see what happens to our money. Here's the die roll game again. You bet $10, you win $45 if you roll a 6, and you lose your $10 otherwise. On the right is a simulation of someone starting with $500 and then playing the game 250 times in a row. Remember, this is just one simulation. It's one possible sequence of wins and losses. And in this particular run, by the end of all the bets, their bankroll is lower than when they started. But a single simulation doesn't prove anything. Simulations include randomness, so every time you run one, you get a different path, different ups and downs. So here's another run. And here's another. And even though each line wiggles in a different way, the pattern is the same. Every simulation ends with less money than the person started with. Not because of bad luck, but because the structure of the game is working against them. Now let's add a simulation of the wheel game. Same starting bankroll, same 250 bets. And this time, the player ends with more money than when they started. So just by simulating the games, not doing any math yet, we already get a sense of which one might be favorable to the player. The second way to evaluate a game is by calculating something called expected value. Expected value tells you, on average, how much money you gain or lose every time you make a bet if you played that same bet over and over again. Let's start with the die roll game. You win if you roll a 6, so the probability of winning is 1 out of 6. The formula for expected value is straightforward. The probability of winning times the amount you could win, plus the probability of losing times the amount you could lose. So here, that becomes 1 over 6 times $45 plus 5 over 6 times negative $10. When we calculate it out, the expected value is about negative 83 cents. That means every time you place this $10 bet, on average, you're losing 83 cents. Not every single time, but across many bets, that's the trend. Now let's do the same thing for the wheel game. There are 4 red slots out of 10 total, so the probability of winning is 4 out of 10. We plug the details of the game into the formula and calculate, and that works out to an expected value of 80 cents. So for this game, every time you make the bet, on average, you're gaining 80 cents. So using this method, the die game loses money over time, and the wheel game makes money over time. The final method for evaluating a game is by comparing odds, specifically what are called the losing odds and payout odds. This method doesn't require any simulations, and it doesn't require formulas. it's just ratios. Let's start again with the die game. We know the probability of winning is 1 out of 6, but what are the odds of winning? It sounds like the same thing, and in casual conversation, we may use words like probability, odds, and likelihood interchangeably. But they are different, and the difference is important for understanding gambling math. Winning odds compare the number of winning outcomes to the number of losing outcomes. For the die game, that's 1 winning outcome to 5 losing outcomes. From there, losing odds are just the reciprocal, 5 losing outcomes to 1 winning outcome. Next are the payout odds. Payout odds measure the ratio of how much you could win to how much you could lose. Here, you win $45 if you win, and you lose $10 if you lose. So the payout odds are 45 to 10. Now to figure out if a game is favorable, we compare losing odds and payout odds. A game is favorable if the payout odds are larger than the losing odds. To compare them easily, we can rewrite the ratios with common denominators. And when we do that here, we see the payout odds are smaller than the losing odds. So the die game is not good for the player. Now for the wheel game. There are 4 red slots with which we would win, and 6 remaining slots with which we would lose. So the losing odds are 6 to 4. The payout odds are 17 to 10. You win $17 if you land on red, and you lose $10 if you don't. Again, we can rewrite both ratios with common denominators to make the comparison obvious. And here, the payout odds are larger than the losing odds. So the wheel game is favorable. It's a good bet for the player. Now let's look at a third game. You watch a basketball player shoot a free throw. You win the bet if they make the shot. If you win 95 cents. If you lose $10. And this particular player makes 91% of their free throws. The payout odds are straightforward, 0.95 to 10. But how do we calculate the losing odds here? Unlike the die or the wheel, we don't have a list of winning outcomes versus losing outcomes. There are only 2, make or miss. In this situation, losing odds are calculated as probability of losing divided by probability of winning. So the losing odds are 9 to 91. Now we rewrite both sets of odds using common denominators just like before so we can compare them directly. And even though the player makes the shot 91% of the time, the payout odds are small compared to the losing odds, so this is not a good bet. Your probability of winning is high, but the reward for winning is not large enough to balance the much bigger loss when you lose. So now let's zoom out and think about an actual casino. Casinos offer all kinds of games. Dice games like craps, machines like slots, card games like blackjack, and even lottery-style bets. And you might wonder, if we use these same 3 methods, simulation, expected value, and odds, are any of these games actually good for the player? The answer is no. All of these games are advantageous for the casino, not the player. So now that we've dug into simulations, expected value, and odds, let's come back to the 3 big misconceptions. The house always wins, but not for the reasons that make great movie scenes. Casinos aren't using hidden technology, they're not hiring muscle, and they're not cold decking players. They win because of math. The structure of the games gives them an advantage, and that advantage plays out over time. So what's the only guaranteed way to beat the house? Don't play.